Welcome to Computer Science 305. This is Programming Languages in our second look at Prolog. So, most of this is a lot of the theory underlying Prolog, but we will eventually get to some code. Since Prolog is such a pretty simplistic language, there's not really that much that we need to be left to talk about. All right, so the main concepts here are unification, the three different views of Prolog's execution model, and then we'll get into the lighter side of Prolog and whatever that means. But it's pretty interesting stuff. So when we start talking about this unification, the first thing we have to understand is what is the true definition of a substitution. So basically all a substitution is just a function that maps a variable to a set of terms, right? So if we have some function sigma, which maps x, the variable x to the term a, y to the term f of ab, then we can say that effectively sigma maps x, as I just said, x to a and y to f of ab. The result of applying a substitution to a term is what we will call an instance of that term. And so if we have something similar to a substitution for g of xy, that would then, if we apply that substitution to g of xy, we get g of a and f ab, right? So we can say that that is an instance of the original term with variables in it, right? So given that, unification, right, is where we take two Prolog terms, T1 and T2, and we're going to unify them. We can say that they unify if there is some substitution, sigma, that makes them identical, right? Such that sigma of T1 equals sigma of T2. So lots of things will unify, some things don't. So the two simple terms, or the two atoms, A and B, do not unify, right? There's no way to unify the atom A with the atom B. We can unify f of xb and f of ay. We can call those unify because x maps to A and y maps to B, making them equal. We can't unify f and g, regardless of if there was some possibility, because f by itself cannot unify with g. We can unify a of xb and a of bxx, right? They unify is just where we map x to b, and so on. The interesting one is that a of xf and a of xf unify where the unifier is the empty set, right? It just nullifies x. And so the reason it just makes x nothing, basically. And the reason we do that is, actually, I think that's the next slide. So if we have, we can have multiple unifiers, right? For any one possible substitution, or sorry, we can have multiple unifiers, so multiple substitutions possible for any one unification that we're attempting to pull off. The problem here is that we have to select one of them. And so Prolog will always choose a unifier similar to, in this case, sigma 1. And the goal here is Prolog will only unify or only substitute enough to make a unification occur, right? So it chooses the minimum, or the what we'll call the most general unifier, right? The more and more detail you have, the more specific it becomes. And Prolog prefers to have this most simple or more general unifier. And so we can say that term x is more general than term x2 if x2 is an instance of x1, but x1 is not an instance of x2. So for instance, when we had parent Fred Y, and we can say that this is more general than parent Fred Mary, right? Because parent Fred Mary is an instance of parent Fred Y, but parent Fred Y is not an instance of parent Fred Mary. So unifier sigma 1 of the two terms T1, T2 is an MGU if there is no other unifier sigma 2 such that sigma 2 T1 is more general than sigma 1 T1. Right. So, more general unification is unique up to variable renaming. So we'll come into that in a minute. So unification for everything, right? Parameter passing, binding, data construction, data selection. We can unify all these things. The system does not care one way or the other. The occurs check. So any variable x in term t unify, right, with x to t. When x and b, so we can say that x and b unify, and MGU would be x is mapped to b. X and f of a g b c unify as the MGU is x maps to obviously f of a g of b c. So anyway, we can continue along, right? There's the unless x occurs in t, right? So all these unifications are great until we see that x occurs, right? So x and f of ax do not unify in particular because do not unify in particular not by x to f of ax, right? Because x is a part of the right hand side, so it's not going to work out. So we can actually run this. If we define append, and let's just see if we can create a new file. We say append we'll go ahead and run that. Okay, we say append x and then a or x. And it gives us this. Actually, that one turned out working. But anyway, so most prologs emit the occurs check. ISO standard says the result of unification is undefined in case that should fail the occurs check. Basically, in this case, right, it shouldn't have worked out, and as we can see, it did not. It just magically allowed it to happen. It's a nasty thing, but we'll talk about why that actually works in a second here. So, there are three different views of the Prolog execution model. We talked about them in the previous lectures, so we'll continue here. So we have the procedural view, implementational view, and abstract view. So procedural view, one way to think about the Prolog execution model is basically we have each clause is a procedure for proving goals, right? So anytime we define a clause, for example, we have P, which is made up of Q and R. To prove a goal, first unify the goal with P, right? So if we have some goal, so when you have when you're at the terminal, and it has the is it question mark colon or question mark dash, that's where you provide the goals, and then our so we have to then unify our goal with P, right? So we have to find something that matches that, and then we want to prove Q and then prove R, and then we have S, right, which is just by itself is to prove a goal, unify it with S. So proof may involve calls to other procedures, calls in quotes here. So we had a simple procedural example, right? We say P is defined as Q and R. Q is defined as S. R is defined as S, and S is just returns true. So if we if we try to unify on P to P, right, returns P, right? So it's like saying there's a Boolean definition for this function P, and it will just simply return P, right? Just as we see here, these are all Boolean functions that just return, if we were thinking this in a procedural way, this is what would happen. S returns true. So thinking about in this procedural way like that is possible, but it leads us to a certain problem, right? One complication of this model is backtracking. So we have to think about how Prolog actually does this, right? So Prolog goes through and explores all possible targets of each call until it finds as many successes as the caller requires or runs out of possibilities. So basically, it's walking through all the facts that it has or other potential functions it needs to use to figure this out. As long as we're continuing asking it for information or runs out. So we consider the goal P, right? It succeeds, but only after backtracking. So we call P on, P. P then is attempting to, then it has to satisfy Q and R. It then calls Q. Q calls S. S returns true. And then it calls R. R calls S, and then it returns true. So it's really what's going on, right? So we have P calls Q and R, Q, S. We have Q, R, then S, right? Makes sense. The other complication is this concept of substitution. We talked about what substitution was earlier, where we define as a part of unification, where we define that we have some function mapping variables to terms in order to find such that if I apply the function to both sides of the equation, they would be equal. Well, when we start out, we have some function or some call that we want to make, P with the value f of y. And so what we have to do is we're going to map, right? So we're finding the MGU, P of f of y to T is applied now to all subsequent conditions in the clause, right? So then that leads us to Q of y, which then constructs a second substitution developed by Q to prove that sigma 1 QY, right, is applied to all subsequent conditions in the clause, which then leads us to sigma 3, which is applied, that's applied to R, and then sigma 3 is generated by R to prove that sigma 2 of sigma 1 of R of Y, right, is equivalent, right? So effectively it gets down, once we've combined all these substitutions that we return to the caller, is that sigma 3 of sigma 2 of sigma 1 of T, right, is equivalent to sigma 1 of P of f of y of T. And that's essentially what's going on. So, but this is the notion here is that this is the hidden flow of information, how all these things are being converted such that we can actually acquire a proof or no proof, right? One of the two. And so that is thinking of everything as a call in a procedural way. An implementational way of thinking about this, right? The implementational view of how Prolog's execution model is actually built, we have to first think of this concept of resolution, right? This is the, so in the background, this is what the actual inference step is, right? Resolution is a logical technique, which I'm not going to go into, but essentially we have a set of a clause and a set of goals, right? So a clause is just simply a list of terms, and then in the case of its effect, it only has one term. And then basically what resolution does is it applies one clause once to make progress on a list of goal terms. So basically it says you have sub is equal to the MGU of head clause, right? So clause is the list. So we take the head of that, we apply, we find the MGU for that, and the head goals, right? So the MGU of clause and the head of the goals. So once we have that, we then say we're going to substitute the tail of the clause concatenated with the tail of the goals. We're applying that substitution that we came up with, and we're going to do this until there's no more till clause and goals, one of the two is empty or both are empty. And so let's say we are given a list of goal terms P of x and S of x, and this rule to apply. So we have P of f of y, Q of y, R of y, right? So the MGU of the heads is x f of y, and we get the resolution step. So we call resolution, that would be P of f of y, Q of y, R of y, that's our clause, right, list. And then we have our goal list, P of x, S of x, right, which ends up being equivalent to Q of y, R of y, S of f of y, right, as we follow this function for resolution. So then we can use this concept of resolution to provide us the base approach for developing a Prolog interpreter. So the Prolog interpreter is a recursive function simply that called solve, right? So we give it a list of goals, and then we ask our base case is if the goals is empty, then we call succeed, right? As in it returns true. Else for each clause C in the program, right, in order of definition, we're going to say if head of C does not unify with head of goals, then do nothing. Else, we're going to solve resolution C of goals. So what this ends up doing is gives us this capability to create a trace, right? So we know that solve tries to solve each of the four clauses in turn. So as we can see here, right, that's our program. It's 4 different clauses. The first works, so it calls itself recursively on the result of the resolution step, which is not shown yet. And then we have the other 3 won't work, right, because the head does not unify with the first goal term, right, because the only one that matches is P matches with P of x, the first goal term. So then we continue along, and then we say, then we start breaking this down, right, the solve, which the first, we then go back and look at the 4 different possibilities, right? And we see that it doesn't match. Q of y only matches 2 and 3, which is why we see that there's a solve there. So it's going to try to solve those, passing in R of g of z or R of h of z, depending on what we have for our Q. Then those go down, and we see if we go through 2, we have nothing that matches g of z. But we can go down through 3, and we have one that matches, so we have nothing that matches R of g of z, but we do have something that matches R of h of z, which is number 4. So then we call solve on that. It's empty, right, because there's nothing left to solve on that. And then we reach success. So that's basically a completed trace for our program. When we collect, so the goal is then we need to then collect these substitutions, right? So we have resolution, we have solve. So we've updated this right now to pass original query along and apply all substitutions to it. What we can see here is that we define our substitution, and then we return the sub of the tail of the clause concatenated with the sub with tail of goals and the sub of the query, the original query, right? So resolution now takes in the actual query itself. Solve takes in the goals and the query, and then if the goals are empty, then we succeed on the query. Else, we do everything else before. Just as we just now are providing more information, right? And now the proved instance is passed to succeed, which is useful. So as we can see along here, we modified this trace now so that it passes in the actual query as it goes along, and then we finally get down to the teal or green looking P of f of h of a, which is the solved query that we expected. So this gives us now the ability to essentially have a full interpreter for Prolog. But there are some issues, right? So the Prolog interpreter is the one that we just showed, is how the original ones worked back in the day. Now they have an actual compiled, a completely different but compiled technique that makes it so that it's a little bit more efficient. But we also know that that the same order, the same way it's doing things must be, all these things must be done in the same order. It's just that it's accomplishing it in a slightly more efficient approach. The last way of looking at Prolog's execution model is in the abstract. And so we can think of any proof that Prolog provides as essentially the walking of a proof tree. And so the interesting thing is a proof tree is also a capture of the order of the traces of proof, right, without the code. So if we go back here, we can see that it actually forms somewhat of a tree structure, and we're walking all the way down until we hit a solve. So, so we know that the root of this tree was then the original query, and nodes are a list of goal terms with one child for each clause in the program. And so then we end up getting something like this, right? So we call solve on P of X, and then that gets us to where we have three nothings, and because, right, we were trying to match the head, and so only one matched the head. We get solve Q of Y, R of Y, and that leads us down to where we had only two things that would match R, which are number 2 and number 3. And so then we go down, we see that nothing matches R of G of Z, but something does match, number 4 matches R of H of Z. And so that gives us this really big tree where we have a whole bunch of nothings, right? And what we really would like to do is be able to trim that down only to the most useful or minimalist version of this tree. And so how we do that is we simplify by we only keep children of a node representing clauses. They appear in the. We want to make sure that they appear in the order, right, from left to right, as they occur in the program. And once it's understood, we can eliminate all the nothing nodes, right? Get rid of all the nothings, and then that will trim down the tree into only what matters. And then that turns out to be something like this, right? The minimalist proof tree that we need. So now that we have that, we have a very efficient way of reaching the end node. So Prolog semantics, right? So if we're given a Prolog program and a query, a Prolog language system must act in the order given by a depth first, left to right traversal of the proof tree, and it might accomplish that using an interpreter like our proof, right? Or it could use some completely different means, which may be far more, we'll say, efficient than the recursive traversal of a tree. This does lead to certain problems, right? So if we devise a program like the rule P implies P and then P, this can actually lead to an infinite non-terminating program if we do a right-to-left, depth-first traversal of the tree, because we'll always, on the left, have a solve P, right? And then the actual termination is on the right side because it's following in order of the clauses. And so it'll be an infinite loop that never ends, which is nasty to say the least. A way around to solve that, right, would be we have an infinite proof tree again, right, but a terminating program. If we say P, then P implies P, right? Because it'll solve itself straight up, right? So it'll solve P and then hit the right, and we'll be done, no problem. So bear that in mind. regardless of how we think about this, each one of these approaches of thinking about the Prolog execution are flawed, right? So the first one had issues with, I think, substitution. The second one had issues with, I can't remember off the top of my head. And then the third one had the issues that we just saw with the infinite proof tree. So the interesting thing about this is they work on the particular examples that we selected, but on some other examples, they would not agree with common sense or with the actual behavior of the Prolog language system. And a great instance of this would be the reverse. So we have a small list of 1, 2, and we're trying to reverse that and unify it with X. And so if we follow the proof tree method, right, we come through and we try to unify reverse 1, 2x. And what would end up happening is we come all the way down here and we'd end up with trying to append an empty list to, and we'd end up with an append empty list to empty list, right? With append empty list 1 empty list. So what this would end up leading to is nothing, right? And this is based on our definition of reverse, which we see right here. Well, the problem with that is actually in the capturing of X, right? So as we can see here, the step that we get to here is wrong because we substitute X for Y, but there's already a different X, right? Elsewhere in the goal list. So this is the nasty problem, right? It's not going to work out as we expected. In reality, what we need to do is we need to rename the variables. So in order to prevent capture, as we talked about in previous lectures. So in order to do this, we use fresh variable names for each clause every time you apply it. So the first application of reverse might be reverse head 1, tail 1, x1, reverse tail 1, so then that calls reverse tail 1, y1, and then we append y1 to the list of head 1 and x1. And the next might be, replacing head 1, the 1s with 2s all the way through. And so we do this so on as many recursive calls as we make. Well, and which will then lead us to the correct answer as we walk all the way down and we solve it, right? So that's great. It will work out. Everything will be good. So obviously there's a solution to all these problems, right? And that's the solution here is we rename everywhere. This renaming step is required for all 3 of the models of execution, right? Every time a clause is used, it must be a fresh set of variable names. This implements clause scope as required. The scope of a definition of a variable is the clause containing it, right? So bear that in mind. All right, so enough of that, right? That's the theoretical aspect of how Prolog works and what's really going on underneath the covers, if you will. This gets us in the lighter side of Prolog. So interesting enough, in atoms, as I believe if you've looked at the actual Prolog lab, you'll see that I use a whole bunch of singly quoted terms for our atoms. I believe they're single quotes. Anyway, but in fact, Prolog treats those as atoms, right? So they are atoms. They just have spaces, so you need to enclose them in quotes. And then you can also utilize uppercase, lowercase letters. It doesn't really matter. And quoted strings can always use, of course, escaped characters like /n/t/ apostrophe, and of course the double backslash, right? So it's all good. We can also get input and output. So if we need to, for example, output a string to the terminal, we can say write. If we need to get input from the user, we can say read and give it a variable. Write takes the value that we'd like to put out or to the screen. Read takes in a variable and or any other term, right? So it's these are simple term input and output. We can also we have the predicate NL, which is equivalent to write a new line, right? So think about that. We can also use write to help us debug. So if you are working on the definition of a rule, you can actually define. You can use write to show each of the individual steps if you need to. We also have the assert predicate. So assert is interesting because whatever you give it, right, the term that you give it, it will add that as a fact to the database. Note, it'll be at the end of the database, which could be interesting to your program and its execution flow. Bear that in mind. There's also the retract predicate. Retract will remove the first clause in the database that unifies with that parameter. There's also a retract all, which removes all matches. The thing about this, though, is these are, using asserts and retracts are nasty because they're self-modifying code. That's always dangerous. It's not safe, nor is it declarative or efficient, but can be tempting, and we'll show that in the very final example. It's always useful for facts or predicates not otherwise defined by the program, and only where the clause in order is not important, right? Finally, when you have consult, right? So when you use consult, it compiles that code into Prolog. So if you read things in through consult, you cannot modify them with assert, retract, or retract all. So bear that in mind. Finally, we have the cut. It's written as just an exclamation point. It's logically a simple thing. It's saying that a goal that always succeeds. It's sort of like true, but slightly different. When it succeeds, it eliminates backtracking. So it's sort of like saying we're going to cut off the rest of execution from this point on. And the way that we're going to use it in this class is simply as the final condition rule, although there are several examples out there in the internet that will utilize it like in the middle of a rule just to continue on, but bear that in mind. So when we put at the end of a rule, right, when we put cut at the end of the rule, it's basically saying that if for example, here we have P, the predicate P that is defined as Q1 through the conjunction of Q1 through QJ. So if Q1 through QJ succeed, the cut does too, and it tells Prolog there's no going back, right? We can't backtrack to look for other possible solutions for Q1 through QJ. It's just saying that, and no backtracking to try other clauses for the goal P that succeeded that way, right? So if it finds one succeeding capability, one succeeding approach, it's done, right? So in other words, the first solution found for a given goal using this rule will be the last solution found for that same goal. So cut just gives us a way to reduce, processing and move forward without having to test if there's more than one possible answer. So, for example, if we had what we see here, right? It's just a simple membership function for a set or a list, and we're saying we're defining the predicate P to be member, and then we have a variable X, and then the list, and then we have write X, right? So normally, if we were to run this with no cut, it would, as long as we kept pressing the semicolon, it would give us, it would walk through the entirety of the list and substitute those values for X, and then would write them out one at a time, and then finally write D at the end, right? When there's there's nothing left. Well, the interesting thing about that is, if we were to put a cut in there, it would go through, find A, substitute X with A, and then write A, and then that's it, right? It would never reach the D level or anything. Once it found the solution, it was done. There is no more continuing on. So the key trick here is we want to be very careful when we use cut, because it's non-declarative and extremely prone to any errors. There are two different kinds of cuts. There's the green cuts, which is where this is to improve efficiency, saves time and space on backtracking, and there's when there are no more solutions anyway. So there's no other solution than the only one that you found. That's called the green cut, right? A red cut is the exact same thing, except for it changes will change the solutions that are found, right? So it reduces the actual number of potential solutions to just one. It's useful and sometimes necessary, but it should be used with caution, as it says here on the slide. So the last piece of this is the adventure game, which I'm not going to write the code out straight up. I've already written it out, but we'll walk through it and see how it works. So one thing you do have to know is how do you actually do comments in Prolog? Well, they're just like Java with the multi-line comment with the /* and //. And then for single-line comments, unlike Java, which uses the double slash, this will use the % symbol, similar to what we found, I believe, in no other languages. Yeah, okay, so just the % will do this. It's in many other languages use that, but we're not going to deal with it today. So anyway, so there's this adventure game. So basically what it is it's like just a text-based dungeon game where the goal is we kind of walk through, and so you have a bunch of different places. Your goal is to find the treasure, avoid the ogre, don't fall off the cliff, right? So there's 6 places you can go. You have the valley, the path, the cliff, a fork in the path, a maze, and a mountaintop. So and then get the gold, don't die. Get the treasure, don't die. So the first thing that we define in here is a set of descriptions, which are 2 things, right? One is the name of the place. The 2 is the description of that place. So you can be, as it said before, in the valley, path, cliff, fork, maze, or mountaintop. Once we have that, we have a predicate that will, or rule that will report your current location. And I believe we can actually write that. Yeah, so we'll go ahead and run that. Okay, so let's say simple. All right, so we load the game up, and then we can assert and then we say report. Right, you're teetering on the edge of the cliff. We can retract. And we can say assert at U valley. And then we say report. Right? So we see that that's working so far. And then we're going to see this next section here, which is all the connects. Right, so these connect predicates establish the map, right? So the map of the actual world that we're building. And the meaning of connect x dir is that if you are at x and you move in a direction dir, you get to y, right? And apparently I cannot spell, as we all know. Direction. Recognized directions are forward, right, and left. So and then we also have to define move, right? And so move just gives you, if you give it a direction, it will print the description. It will move you in that direction, then print the description of a new location, right? Note there's a final cut here. So what it basically says is the second clause for move will be used only if the first one fails, which happens only if the direction that you provided was not a legal move. So if we go back up to our connect, right, not all things have all possible legal moves. For example, forward, left, and right. Only a few do. So you can't go left or right at the valley. And you can't go forward at the fork. So, and then if you're at the mountaintop, you can't go in any direction. And then in the maze, you may only be able to go left or right. You can't go forward. So, bear that in mind. If the argument was not a legal direction, right? So it says it's not going to allow you to go beyond, right? If you gave it a legal move, a legal direction, it will just go that direction. Otherwise, what it's going to do is it's going to print that is not a legal move, and then report where you are. And then we define some shorthand for moves. We have forward, left, and right. So as we can see here, this is where we are. Then, so what we should be able to do is we'll go and run some more assertions. So we can say assert at you. I think I'm already there. Yeah, okay, we're there. So we can say forward, right? And now I'm on the path. I have ravines on both sides. I can say forward again, right? I'm now at the fork in the path. If I say forward one more time, that gives me this is not a legal move. You are at a fork in the path. So then we need to define, like, so it said that I mentioned if you meet the ogre, then you die. So we have to define that. Again, we're going to use the final cut, right, to prevent us from. So if we reach the same location where the ogre is, we're going to write that the ogre sucks your brain out through your eye sockets and you die. Then we're going to retract our location and then assert that we are at done, right? The game's over. On the other hand, if we are not at the same place as the ogre, then nothing happens, right? So the cut will prevent us from reaching this part if this entirety of this logic succeeds. On the other hand, if it doesn't, then we are just going to continue on because, you know, obviously we don't die if we're not where the ogre is for this set of logic. So now, similarly, we use the same type of cut when we detect we're at the same place as the treasure, right? Because then that's when we win, right? So if we're at treasure and the treasure, there's treasure here, congratulations, you win. Retract our location, move ourselves to done. And then otherwise, if that's not the case, then we don't do anything when treasure is called. So finally, if we're at the cliff, right, we claim you're at the cliff, right, that you fall off and die, retract and assert, retract where you are, assert that you're at done, and then cut off all the solutions if all that succeeds. Otherwise, we do nothing, right? You're not at the cliff. Okay, finally, not finally, but we get closer, right? Now we're at the main loop, right? So the main loop, the first part of it is we're going to detect, are they at done, right? Have you at some point in time been moved to the done? If you are, then we write thanks for playing, and then we run the cut and stop there. Otherwise, we have the loop, which is if we're not done, we need to get a move from the user, make it, and then run all of our special behaviors, and then we'll just repeat the loop. So how this works is it says, right, ask them for their next move, read in move. We then call move, right? So they type in forward or left or right, and then we call that, right? The call is a special predicate that tries to prove X as a goal term. And then we run our special logic for ogre, treasure, and cliff. And if and then we run main, right? So the interesting thing is if ogre, treasure, or cliff are true, then that will all three of those move us to done. And then we check at main is are we at done? If we are, then we say well, thanks for playing. And then we cut it off from there. Otherwise, we continue on with main, right? Because that's not the match that we were looking for. All right. So now, and then it goes back to the main loop, right? So once we've done that, right, we also need to set up the initial starting point for the game, right, with the go predicate. And this is going to retract all at things things that we've already put in there, right? Because the game always ends with "at you done." We're going to remove all that. Where the ogre was and where treasure is and all that type of stuff. Then we're going to make the assertions. We're going to put the U at the valley. The ogre is at number 3 block in the maze, and the treasure is on the mountaintop. And then we print out the intro part to the game, report where you are, and then start the main loop. So if we were to run this, we can say go. Oh, and note, when you do make moves, you have to put a period at the end. Then it says, you are in a pleasant valley with a trail ahead. We say, I'm hoping that eventually it gets me to next move. It may just not work, and I may have made a mistake somewhere in there. But apparently it's not telling me I need to do something. Did I miss something? Maybe. Let's take a look. Let's see, main, next move. Apparently it's giving me an issue, but we'll move on from there. So here we are, next move forward. You're on a path with ravines on both sides, so we say forward. And then, so we're at a fork in the path, right? We say right. There is a treasure here. Congratulations, you won. Thanks for playing. True, right? So, it's a little wonky, but it does work. Anyway, so I would suggest taking a look at that. This will be online and linked so you can go and take a look at it. And other than that, I look forward to seeing you all in class. Have a great day.